we're going to jump in. So I'm going to start off with some basics. So if you've done chemistry before, this stuff, you're going to be like, oh, this is easy. Why am I here? Really important we go over it again. Pardon me. And for a lot of people, this is the first time you're learning it. So you'll be like, oh, I haven't done this before. I'm not sure what's going on. So it's really important we go over this again. And for those who have done it, it's really good revision. So there are some key definitions that you do need to know, and you need to know these all the way through. So a lot of this first area study, you will know this content. You might think, oh, how am I going to remember this content in 24 months' time when I'm sitting that exam for year 12? You just do. This stuff comes up all the time, and it's why we learn it first, because we want to teach it to you, and then when it continuously comes up, you just remember it. It just becomes part of your memory. So atoms, basic building blocks of matter. We know that. We're cool with that. Elements, materials containing a type of atom that cannot be broken down. Compounds, materials containing different types of atoms in fixed ratios. And then molecules are substances in which two or more atoms are combined. So essentially, compounds and molecules are very close to each other, but molecules are generally from the same atom. So think of it like an oxygen molecule. So oxygen is O2. So oxygen in the air is referred to as O2. What that means is there's two oxygen atoms connected to each other. Whereas a compound is something like a salt. So salt, typical table salt, is sodium chloride. That's what it is. And sodium chloride is NaCl. So one atom of chlorine, one atom of sodium. Oxygen, two atoms of oxygen. This is a molecule. This is a compound. So you've got a compound which has two different atoms, or more than that. You can have multiple. Molecules, you have one. You have one type of atom. Structures of atoms. So really important that we understand that atoms are made up of subatomic particles. A positive nucleus is surrounded by negative electrons. So the protons within the nucleus are what give the charge. The neutrons have no charge. The protons and neutrons both give atomic mass, so they both give all of the mass of the atom. So if the atom weighs X amount, it's all the protons and the neutrons. The electrons have nothing to do with it. The electrons are negatively charged. They're a lot smaller than the protons and neutrons, and they orbit the nucleus in a cloud of electrons. And we have this thing called electrostatic attraction between the nucleus and the atoms that kind of holds it together. And that's sort of a really key concept to understand, that the positive charge from those protons keeps those electrons held within that sort of atom area. Now, give me a second. I'm just going to do it by my nose, because otherwise I'm going to sniff this whole hour. So just give me 1 second. All right, let's jump back in. So when we classify atoms, there's two important things that you need to know. You need to know an atomic number, which is this one here. It's this 26 right here. And there is a mass number, which is this one here. Now, really important. An atomic number is the number of protons, and the atomic number refers to where it is on the periodic table. So, pardon me. That's me. The atomic number essentially is where it is on the periodic table. So this will be element 26. This is the name of the element. Pardon me. Apologies, just out here struggling. And then you have your mass number, which is the number of protons and neutrons. Now, notice how this is a decimal. You can't have a decimal number of protons and neutrons. You can only have a whole number. However, we have separate... I'm very much struggling. Apologies. We have a separate number of protons and neutrons for same atoms. Sometimes the atom will have a different number of neutrons. So this iron here might have 26. It'll always have 26 protons, but it'll always have a different number of neutrons. Oh, I'm actually struggling. I'm really sorry. I obviously woke up on the wrong side of the bed this morning. And so what happens here is we have some with all of them have 26 protons, but some of them have different number of neutrons. So you have some with 30 neutrons, some with 29 neutrons. And so essentially what we get is this number that says this is approximately the middle value of how many protons and neutrons we have. And we just use this as sort of the relative mass. And we'll discuss this in a little bit. But these are the two important numbers when looking at a periodic table. So this is the mass overall. So it's the protons plus the neutrons. This is just the protons. So this is where it is on the periodic table. And the protons tell you what atom you have. So if I have 26 protons, I'm going to have iron. Now, forms of atoms. We have, as I said before, isotopes. So isotopes are exactly what I was just talking about. As you can see here, we have carbon, and we have carbon-12. Carbon-12 has 6 protons and 6 neutrons. We have carbon-13, which has 6 protons and 7 neutrons. We have carbon-14, which has 6 protons and 8 neutrons. So you've got two different forms. You've got three different forms. So you've got all three with 6 protons, but then the neutrons change. And these are isotopes. They're all carbon. They all will act extremely similar. However, some of them just have slightly different number of neutrons. And notice how we have percentages here. Nearly 99% of these are carbon-12. So the relative mass of this isotope is probably going to be around 12. Might be like 12.02 or 12.01. It's going to be pretty much 12. Then you've got 13 with 1.1%, so it's not going to be like the relative mass of this is not going to be 13, nor is it going to be 14 at less than 0.1. Then you have ions, which are atoms with a different number of electrons to protons. So when an atom is stable, it's going to have the same number of electrons and protons. So if you think about it, if I have 6 protons, I've got 6 positive charge. And if I have 6 electrons, I have 6 negative charge. They cancel out. I'm just a neutral atom. Whereas if I lose some electrons or I gain some electrons, so in this case here, we lost some electrons here. So we lost this last electron here. Essentially what we end up with is a charge of +1 because I have more protons in the middle than I have electrons on the outside. Now, if something has a positive charge, we call it a cation. If something has a negative charge, we call it an anion. I always like to think of this as happy cat, and then anion as the opposite. So if it's happy and it's positive, it's a cation because cats are happy. May not always be a thing, but that's kind of how I go about remembering it. And then we have this new concept, and this is a really interesting concept. So we have what is called critical elements. So we think of this as, if you look at your periodic table, which we'll go through in a second, this is your periodic table. You have all these elements on this periodic table. If you think about this periodic table, some elements are more abundant than others. Some elements are necessary in everyday use more than others. So what about elements being endangered? It's not necessarily an odd concept. We just say there are less of this element and now it becomes endangered because maybe we want to utilize it lots, but it's not there. So it's just like animals. If it's extremely desirable, but it's extremely hard to obtain, then we call it endangered. So there are 4 individual groups of critical elements that VCAR wants you to know, and we're just going to go through the first 2 briefly today. So essentially, you need to know a brief summary about all 3 of these, so that if it were to come up in an exam or a SAC, you could just discuss them. So these are the 4 you need to know. You need to know, so we're going to go through the first 2. We're not going to go through all 4. You need to know helium. So helium is the number 2 on the periodic table. So if we go to the periodic table, it's number 2 up here. Helium is has an extremely low boiling point, and it's always obtained as a gas. And this makes it useful in various lines of work. We don't worry about what lines of work this is useful in, but essentially, because of its low boiling point, it's always a gas. You can cool it right down and it'll stay a gas. Most things you cool down won't be a gas. They'll either be a liquid or they'll be either be a liquid or a solid. Whereas when you cool helium down, it stays a gas. Helium, when released as a gas, it just rises. So you know how you get helium balloons and they just go up and up and up? If you just release helium, it just rises, just like that. And essentially, it's so easy at rising that it will actually rise to the point where it leaves our atmosphere. And once it leaves our atmosphere, it's actually not on this world anymore, and it goes out into space and it's no longer usable. So that's why we call it a truly unreusable gas. So when you obtain it for the first time, then you utilize it, it goes, it disappears. So although it is the second most abundant element in our world, it is now known as a critical element because we need it for so many things, but it just disappears. Same thing happens with sort of phosphorus, but a little bit different. Essentially, phosphorus is used in everything to do with DNA. So everything has DNA. Plants have DNA, humans have DNA, animals have DNA, anything that's living has DNA. So because of this, and phosphorus being the backbone of DNA, it's obviously pretty necessary in everything. And it's extremely necessary in plants. So because plants grow so quickly, we need lots of it. So we like to use it in like fertilizers. But obtaining phosphorus is becoming really hard. And what I mean by that is they say that when you obtain 100%, so let's just say we grab 100% phosphorus from wherever we're obtaining it, when we actually get it into the product we want, like we get it into the fertilizer, we get it into the tablets, whatever it is, there's usually only about 20% of it left. So 80% is lost in the chain of production, which means it's really, really bad at being used. And because of the huge increase in crops as our population grows and the increase of demand of phosphorus-rich fertilizers, phosphorus has actually become endangered. It's really hard to obtain it. Then when you do obtain it, it's really hard to get it into the desired product. So phosphorus has become a critical element and an endangered element for that reason.